In our previous sessions, we explored the concepts of populations and samples, and how statistical inference allows us to make predictions about a population using sample data. We also discussed the central limit theorem, CLT, which tells us that the sampling distribution of the sample mean tends toward a normal distribution, regardless of the shape of the underlying population, especially as the sample size increases. Building on these ideas, in this session, we will examine two important probability distributions: the normal distribution, the t-distribution. Both serve as sampling distributions for the sample mean, and are critical tools in estimating the population mean, mu, from sample data. We will explore when and how each distribution is used, especially in the context of sample size, n, and knowledge of population variability, sigma. Normal distribution and t-distribution in statistical inference. In inferential statistics, we use sample data to estimate unknown population parameters, like the mean or proportion. Two common sampling distributions used for this purpose are: 1. Normal distribution assumes that the population standard deviation, sigma, is known or the sample size is large, typically n is greater than or equal to 30. The sampling distribution of the sample mean is approximately normal, by the central limit theorem, used to construct confidence intervals and conduct hypothesis testing when conditions are met. 2. T-distribution used when the population standard deviation is unknown and the sample size is small, typically n. It's similar to the normal distribution but has heavier tails, accounting for more variability due to smaller sample sizes. Becomes closer to the normal distribution as sample size increases. Importance of sample size. Large sample size, n is greater than or equal to 30. The sample mean follows a normal distribution regardless of the population's distribution, central limit theorem. The normal distribution is often used for inference. Small sample size, n, greater uncertainty due to unknown population standard deviation. The t-distribution is preferred, as it adjusts for this extra variability. Degrees of freedom, df. Degrees of freedom, df, reflect the number of values in a sample that are free to vary when estimating a statistical parameter. For a t-distribution, the degrees of freedom are typically df equals n-1, where n is the sample size. As df increases, the t-distribution becomes more like the normal distribution. When both the population mean, mu, and population standard deviation, sigma, are known, we can use the normal, z, distribution to make statistical inferences about the sample mean. This situation typically arises in theoretical studies, quality control, or in large-scale, well-documented processes where population parameters are established through long-term data. In such cases, the z-statistic is used. The t-distribution was developed in 1908 by William Seeley Gossett, a statistician working for the Guinness Brewery in Dublin, Ireland. Gossett was tasked with improving the quality control of the brewing process using small sample sizes, but he found that the normal distribution was not accurate for small datasets, especially when the population standard deviation was unknown. To address this issue, he derived a new distribution that accounted for the added uncertainty in small samples. Due to Guinness's strict policies against publishing research, to prevent competitors from benefiting, Gossett published his work under the pseudonym, Student. That's why the distribution is still known today as the student's t-distribution. The t-distribution became a cornerstone of modern statistics, particularly in hypothesis testing and confidence interval estimation, especially when working with small sample sizes and unknown population variance. When the population mean, mu, is known but the population standard deviation, sigma, is not known, and we are working with a sample, we estimate sigma using the sample standard deviation, s. In this case, the t-distribution is used instead of the normal distribution, because the estimate introduces extra variability, especially in small samples. The t-statistic is calculated as shown above. When neither the population mean, mu, nor the population standard deviation, sigma, is known, we rely entirely on sample data for estimation. In this case, we estimate mu using the sample mean, x bar. We estimate sigma using the sample standard deviation, s. We use the t-distribution for inference. The t-statistic is calculated as shown above. The table summarizes the three main scenarios encountered when making statistical inferences about a population mean using sample data. When both the population mean, mu, and standard deviation, sigma, are known, we use the normal, z, distribution. This is a theoretical or ideal case, often used in controlled environments like quality control. When mu is known but sigma is unknown, we estimate the standard deviation from the sample and use the t-distribution. This situation is less common but still valid, especially in experimental settings with a known target mean. When both mu and sigma are unknown, which is the most common in real-world statistics, both are estimated from the sample, and the t-distribution is used to account for the additional uncertainty. Each case uses an appropriate formula to compute the relevant test statistic, z or t, which helps in constructing confidence intervals or conducting hypothesis tests about the population mean. The claim of the factory that the mean lifespan, i.e. mu, is 1,000 hours and the population standard deviation, i.e. is 40 hours, is based on past data. To test the claim, a sample of size n is taken and the average lifespan of n samples, x bar, is calculated. The z statistic is calculated by substituting the given value of the parameters into the equation. A nutritionist wants to examine whether the average body weight under a new diet plan differs from the standard value of 70 kg. Since the population standard deviation is not known, a sample of size equals 10 is taken, and the sample mean, x bar, and sample standard deviation, s, are calculated from the observed data. The equation of the sample standard deviation shown in slide 6 can be used to calculate the value of s. The t-statistic is then calculated by substituting the known and sample-derived values in. The z and t statistics are powerful tools that allow us to make informed decisions about a population mean using sample data, especially when direct measurement of the whole population is not feasible. These statistics are used in 3 key ways. Point estimation. The sample mean, x bar, serves as the best single estimate of the unknown population mean, mu. Interval estimation. By constructing a confidence interval using z or t statistics, we can estimate a range of values within which the true mean is likely to fall, with a specified level of confidence. Hypothesis testing. Z and t statistics help test claims about the population mean by comparing the sample mean to a hypothesized value, leading to decisions based on statistical evidence. Overall, these methods form the foundation of statistical inference, enabling data-driven conclusions and predictions in science, industry, and research.